Good morning, everyone. Welcome to lecture 13. So, in the last class, we were doing polar decomposition, right? And recall that the deformation gradient f was decomposed into multiplication of rotation tensor and a symmetric positive definite tensor. There are two ways to do it, and it's a unique decomposition. Okay, and u we wrote it as summation over I lambda I Ri tensor product Ri, that's little ri, which are the eigenvectors of U also, whereas V was summation over I, same eigenvalues, but the eigenvectors are Li tensor product Li, where this Li is actually big R times little ri. Okay, and we also saw the physical meaning of these two decomposition. So we said that if we have a reference configuration, then you can think of three lines here, which are the eigenvectors of U, and they are little r1, little r2, little r3. So first you apply U, and what happens is that these three lines, being the eigenvectors, do not change their orientation, but they just get stretched. So this is by lambda 1 r1, this is by lambda 2 r2, and this one is by lambda 3 r3. And finally, it's the rotation tensor, the local rotation tensor, which rotates. Okay, but understand that it's the local rotation tensor, it's not the rigid body rotation tensor, because this local rotation tensor changes from point to point. So because of this local rotation tensor, the local infinitesimal lines, they are going to change their orientation. Okay, so this is lambda 1 big R into little r1, and this is lambda 1 big R little r2, whereas this one is lambda 3 big R little r3. Okay, and to see the other decomposition is you first apply V. So when you apply V, then it's those three r1, r2, r3 only, which, sorry, you have to first apply rotation because it is VR, no? So first you apply rotation, local rotation, so you have that body again, and due to the local rotation, those three lines are going to change to, let me make it a bit more rotated, yeah, like this. So these three lines change to big R, little r1, big R, little r2, and big R, little r3. And you can understand that they are also your L1, L2, L3. And likewise here also, this is lambda 1 L1, this is lambda 2 L2, and this is lambda 3 L3. So in the other decomposition, we first apply rotation and then apply this V, and V part just stretches these L1, L2, L3, to finally get the same result. Okay, so that's the physical meaning of R, U, and V. All right. You see, this picture also allows you to write this rotation tensor as big R equal to Li tensor product little ri. Why is that so? Because you see, it is the little ri's which are getting transformed to little li's. And you know that for to uniquely represent a second order tensor, you just need to show how any set of three linearly independent vectors are getting transformed. And this way you are showing that little r1 is going to little l1, little r2 is going to little l2, and little r3 is going to little l3. Okay, so this is how you can write your rotation. And this also means if you want to get your big F, then you see what is happening. Big F is the total, no? So from the reference, little r1 is finally getting converted to lambda 1 L1, and little r2 is finally getting converted to lambda 2 L2, and little r3 is getting converted to lambda 3 L3. So this big F you could also write as lambda I Li tensor product little ri, and here you have to write that summation explicitly. So that's the tensor form for big F. Okay, I hope that this thing is clear to everyone. Okay, there is no question. If you have any question, of course you can ask me. But this is how you can write your big R, big F, and then in the above you also wrote it for U and V. Okay, so let's proceed further. So with these notations for the different second order tensors, we had also seen that the lambda, for example, of a line element at n x, or this is getting converted to, I mean, this is equal to u square nx dot with nx, right? And you have to take the square root. And similarly, you saw that cos theta y, for example, the deformed angle was u square nx1 dot with nx2, where these two are the directions of the two line elements between which we want to measure the angle. And this is then divided by, we can simply say lambda nx, sorry, lambda n1x and lambda n2x. Okay, so what you see is that it depends on u, right? Also the change in volume, for example, dvy was determinant of u into dvx. So these are all very rightly done, because you also saw from the picture that it's only the u part which is responsible for inducing strain, change in length, change in angle, change in volume. The rotation part is simply rigidly rotating the local neighborhood of a body. Okay, so the local rotation part does not induce any strain, and therefore in these formulas it is just u which is showing up. All right, and you know this. because u square is, okay, maybe I can write it a little more nicely below. What you saw is that u square is actually f transpose f, right? And f was big R into u. And similarly, you can show that v square is ff transpose, right? Where the decomposition is the following, isn't it? So this, because you see in this decomposition, u is coming on the right, right? It's r times u, so u is on the right, whereas here v is on the left. So they also have a name. This is called right stretch tensor. Okay, this is simply right stretch tensor, whereas this v is called left stretch tensor. All right, because of the location, you see the way it is there. And this u square has got a name also, that is denoted by c. Okay, everywhere in the book you will see it is denoted by c, and v square is denoted by b. And since c is being formed by the square of u, which is a right stretch tensor, this is also called right Cauchy Green tensor. Okay, whereas this is called, you can guess, left Cauchy Green tensor. So I think you can see why they are called right and left. All right, and why u is called a stretch tensor? I mean, so that is quite clear, no? Because u is inducing the deformation, and in the eigen decomposition of u, you saw that the line elements are just getting stretched by lambda 1, lambda 2, lambda 3. So therefore, although u also induces shear strain, it is not just a stretch, but it also induces shear strain, because in the formula of shear strain you can see u is appearing, but by name we call it stretch tensor. Okay, okay, let me see if there is any question so far. Okay, there is no question. Very good. So having done that, the formulas that we have derived till now, these have Lagrangian nature, no? Because they are taking as an input the directions which are in the reference configuration, the directions of the line element in the reference configuration. So these are Lagrangian in nature. So the formulas are Lagrangian in nature. You can similarly think of relating the deformed line element to undeformed through the inverse map, isn't it? So, for example, we have seen that dy is equal to f dx, right? And that means d small x we can write as f inverse into dy. And you see from here, f dx is same as r times u dx. So if you try to find out the magnitude of dy, then that's equal to magnitude of r times u dx. And r being a rotation, it does not change the magnitude. So this is also equal to u dx, right? So, and of course, this also means that if you, for example, yeah, I mean, you can finally write this as this dy, the final length, is equal to dx. Take dx outside, and then you write here u into nx, isn't it? Where, so here basically dx is equal to nx times mod of dx. So I hope that all of you are okay with this formula. This thing inside the red circle should be clear to all of you, right? But you see here, what you're relating is dy with the referential material line elements, the orientation in the referential line elements. You can likewise think of an inverse kind of thing. So from here, dx is then, and if we use for f vr, then f inverse is r inverse v inverse into dy. Okay, so if we now take the mod on both the side, then dx is simply equal to v inverse dy. Okay, and then if you write dy, so if I write dy as ny, okay, so ny is the deformed orientation, is the orientation of the deformed line element, and then mod of dy. If we write it like this, then you put this dy over here, and what you will get is dy into v inverse times ny. So you see that in this inverse representation, what you have is v inverse. So if you compare this box with the red box, they are kind of inverse maps. And you see that in the direct, it is u which is coming, and in the inverse, it is v inverse which is coming up. Okay, so the role of u is actually taken over by v inverse. And that's also quite clear from this formula, that you see in the inverse map, it is v inverse which is present. It is v inverse which is to act on dy. Okay, so, and you know, for example, if you try to work out the stretch, so from here only you can see what is dx by dy. That's this v inverse ny mod, which you can also write as square root of V inverse ny dot with V inverse ny, isn't it? Which is same as V inverse square ny dot with ny. And you see, what is this? This is 1 by lambda, right? This is actually lambda inverse. But now you are working it out at material point y, and in terms of ny. But that's lambda inverse, that is the inverse stretch. So this formula is now in terms of a line element located in the deformed configuration at the point y and directed along ny. So ny is the direction of the deformed line element. So can we not say this to be Eulerian representation, right? So this is like the Eulerian representation. Because the arguments are all sitting in the deformed configuration. That's why it's an Eulerian representation. And it is because of this reason, see, because in the Eulerian representation it is V coming up, right? So yeah, it is V inverse square, okay? V inverse square. So that's the reason why V is also often called Eulerian stretch tensor. Whereas this U is called Lagrangian stretch tensor. Okay. So Subham is asking what is V inverse square? It is simply V inverse whole square. V inverse into V inverse. All right. I hope that this is clear to you. You see, how did I do it? I bring this V inverse on the other side, then it becomes V inverse transpose. But V being a symmetric tensor, V inverse is also a symmetric tensor, and therefore V inverse transpose is same as V inverse. And therefore you have here V inverse into V inverse, which is V inverse square. Okay. You see, likewise, you can also write down the formula for theta, but in the reference configuration. You recall that we had cos theta y equal to u square nx1 dot with nx2 divided by lambda of nx1 into lambda of nx2, isn't it? So this was, it's of course a Lagrangian formula because the inputs are the orientation of line element in the reference configuration, okay? And what it is giving you is the angle between those line elements in the deformed configuration. You can likewise think of an inverse map. So you can derive that very easily. Just like we did this, we can also derive the other one. And it turns out cos theta x, for example, would be V inverse square, okay, into ny1 dotted with ny2, all right, and divided by this lambda inverse of ny1 into lambda inverse of ny2. So you can see that this formula is Eulerian. And again, it is V inverse square which is coming up. Instead of U square, what you have is V inverse square. All right. So that's some, the just to show you that the role of u is taken by v inverse in the inverse map. Okay. Okay, so there is a question, can't we write the inverse map in terms of u? Well, you can think of doing that, but let us see what you're getting. Um, so here, it's a good question. So what you're saying is that why don't I do it as dx equal to ru inverse into dy. So this is then u inverse into r inverse into dy, right? So what you see here is that you have here, I mean, u inverse is not acting directly on dy. U inverse is acting on r inverse dy. Okay. Whereas here it is v inverse which is acting directly on dy. Therefore, it is more convenient to write in terms of v inverse. And also, when you worked out these formulas, no, these Eulerian formulas, you can see that it is v inverse which is appearing in a very convenient way. And of course, you could have thought that because v and u are finally related, right? So you could have thought that okay, v is r u r transpose, then why don't I write v inverse as r times, sorry, so v inverse is, yes, v inverse is r times u inverse into r transpose. So you might think of substituting v inverse here in terms of u inverse. So you can do that, but you see you have that nasty r also appearing. That is something you are not liking now. So directly in terms of v it is simpler. And also you see when you come to this picture, u, look at this here, u is directly taking the referential line element as input. And here you see v inverse, when you do v inverse, no, so v inverse is taking as an input the line elements in the deformed configuration. So input to v inverse is the deformed line elements, and therefore it's a v inverse which is the Eulerian, which has the Eulerian nature. Okay, u inverse, you see u inverse is this thing, this is u inverse. What is input to u inverse? It's not the deformed line elements, it is the intermediate line elements. So therefore it is not Eulerian. Is that clear, Toiba? Toiba Noor? Okay, and also others, I think. So that was eliminating question, of course. All right, so having seen this, we are just talking of stretch tensor. What do we define strain to be? So we haven't, what about the strain tensor? What would be the strain tensor? So U and V have, it has stretch in it. And of course, shear strain is there, but stretch is there. How to extract strain from those U and V? For example, think of this deformation. You are going from reference to deformed. So you have F. Suppose that deformed is equal to reference. Okay, if deformed is equal to reference, then what will be f equal to? So in that case, f will simply be identity. Okay, and when you work out the polar decomposition, it is simply I into I. So this means u is equal to v is equal to r is equal to identity. All of them are identity. So what you see is that this u and v is not zero when there is no deformation. So when the deformed configuration is same as reference, which means there is no deformation, then u and v are not zero, right? But we know that the strain, when we define, if there is no deformation, then strain is zero, right? So that kind of tells you that we might think of strain to be u minus I, isn't it? It's one measure of strain, correct? And indeed, that's how strains are, defined. And there are several ways to see. Basically, what we want is to have a strain tensor which is vanishing in the reference configuration. So we want to have a definition of a strain tensor which is vanishing in the reference configuration. And there are several such ways. So there are several such ways. One of them is half of, for example, u square minus identity, or you can also generalize it to write as half of, sorry, not half, but 1 by m of u to the power m minus identity. This is another measure of strain. Or you can write it as ln of u. So ln of u is also vanishing when u is equal to identity. So ln of identity is 0. It's the zero tensor. Okay. So these are all qualified definition of strain, because you want strain to be 0 when there is no deformation, or whenever there is rigid body motion, you want strain to be 0. Okay. Whenever there is rigid body motion, you want to have a definition of strain which is 0, and indeed these will be 0 for rigid body motion. See, when you work out for rigid body motion, the map is simply the following: y equal to big R of x plus c, where c is denoting the rigid translation part and big R is the rigid rotation part. Okay, so c is the rigid translation and big R is the rigid rotation part. And from here, when you work out the deformation gradient, big F, that turns out to be R. Okay, which means you can write it as big R into identity, or you can write it as identity into big R, which simply means that from here u is equal to identity, and from here v is equal to identity. So you can see that for rigid body motion, indeed u and v are identities. The other way to see that u is identity is simply work out this thing, no? So u square is f transpose f, and f is r, so this is r transpose r, and that's simply identity. So u square being identity, that means u is also identity. Okay. So what you see is that for rigid motion, u and v are identity, so you must subtract identity from it to get 0, right? So that's why you have these definition for strains, which for finite rigid body motion becomes 0. And they have, all of them have got a name. Okay. For example, this this thing is called green Lagrange strain tensor. Okay, green Lagrange strain tensor. Whereas this thing, where your m is integer, by the way. Okay, m is any integer. So this thing is called generalized green strain tensor, or generalized green Lagrange strain tensor. Okay, in the book it says generalized green tensor, green strain tensor. Whereas this one, this ln of u, so that is called logarithmic strain tensor, or Hanke strain tensor. Okay, you can say it as Hanke. So these are just some name, and you'll find it being used in books. Okay, or logarithmic strain tensor. And you see that each of these strain tensors have the same eigenvectors as of u, because they are formed by powers of u, isn't it? Therefore, each of them have the same eigenvectors as that of u. And it's also quite easy to work out the eigenvalues, for example. So let me just write here. So if you think of eigenvalues, then half of u square minus identity. Can someone tell me what will be its eigenvalue? If u has eigenvalue lambda i's, then what is the eigenvalue of this tensor? See, I just said that it has the same eigenvector. So why don't I multiply this with little r I and see what we get. So this is half u into little r I minus identity times little r I, which is same as little r I, right? But u times r I is lambda I into r I, and then you have another u again multiplied, so you get lambda I square into r I. So finally this becomes half lambda I square minus 1 into Ri. So you can see this is the eigenvalue. Okay, so whenever you have a tensor formed by powers of the original tensor, then the eigenvalues also have the same form. Similarly, for 1 over m u to the power m minus identity, so for it the eigenvalues, you can make a guess, it is 1 by m lambda I to the power m minus 1. And for ln u, again you can make a guess, it is simply ln of lambda i's. Okay, so these are, all these strains have a Lagrangian flavor, right? Because they are in terms of u. You can likewise think of Eulerian strain tensors, right? Which of course will be in terms of v inverse, right? So Eulerian strain tensor therefore have the corresponding forms, which is half of I minus v inverse square. Okay, or a more general is 1 over m into identity minus v inverse to the power m, or ln of v. Okay, and each of them have the similar name. So this is called, of course this is not the green tensor, green strain. It's not the green Lagrange strain tensor. It is called Alamansi strain tensor. Okay, Alamansi strain tensor. So just some names, okay, but it is good to get used to them. And this is obviously generalized Alamansi strain tensor. Okay, and this is simply logarithmic strain tensor. And you can again think of the eigenvalues, right? For example, for this one, the eigenvalues is half of 1 minus lambda I inverse square. This is 1 by m of 1 minus lambda I inverse to the power m, right? And this is simply ln of lambda I. Okay, so I think that it is clear to all of you. Okay, so once we have these strain definitions, um, you can also think of writing it in terms of displacement, for example. So right now it is in terms of u, but you can also think of writing it in terms of displacement. For example, the most popular, I mean, one of the popular one is the green Lagrange strain tensor. So the green Lagrange strain tensor, that's half of u square minus identity, right? Which is same as half of f transpose f minus identity. And then for f, you substitute I plus grad u, and you then simply get half of grad u plus grad u transpose plus grad u transpose into grad u. Okay, so that's a green Lagrange strain tensor. And from here, you would notice that if you neglect the quadratic part, then this becomes half of grad u plus grad u transpose, which is the strain tensor that we have used in undergraduate course. And this is also called infinitesimal strain tensor. Infinitesimal strain tensor. Okay. Likewise, if you think of the Alamansi strain tensor, that's half of I minus V inverse squared, no? So that's same as half of I minus V square and take the inverse. So V square is FF transpose, right? So this becomes half of identity minus V square, which is FF transpose. And then you take the inverse of it. And let's see what is this. So this is half of identity minus FF transpose. So FF transpose will be I plus grad u into I plus grad u transpose, right? And then you take the inverse, which is same as half of I minus I plus grad u transpose inverse into I plus grad u inverse, isn't it? And of course, now you are stuck. What do I do with the inverse of this tensor? But you can write it as half of I minus identity minus grad u transpose. So using that binomial expansion. Okay, and then you have this big O in grad u square. So you have this thing multiplied by identity, again a minus sign of grad u, and then again you have this big O grad u square. Okay, so you see we are doing consistent Taylor's expansion, and we'll finally just drop out the grad u square term just to see what is its approximation if we just keep the leading order term in u. So now work out the multiplication, and you will see that it is half of identity minus identity minus grad u transpose minus grad u, right? And then you have the remaining term, which is big O grad u square, isn't it? So you see, this is how it has come. This into this is coming here, then this into this is over here, and this into this. Okay, I think it's getting messy, so I'll use another color. So okay, maybe from the top, this into this, that's here. Okay, and rest all are inside this big O. And you further work it out, and then you can approximate is as half of grad u plus grad u transpose. So you can see that the significant term, that is the linear in u part, is the same for both these strains, isn't it? It's the same for both the strains. And it turns out all the definitions of strains, when you linearize it in u, displacement u, it gives you the same infinitesimal strain tensor formula. They all give you the same infinitesimal strain tensor that we have used in undergraduate class. Okay, so we get back the infinitesimal strain tensor. So you can show it for other measures of strains also. Okay, if you see the book, it has got another definition of a strain, a more general definition of a strain. So obviously I'm not going to talk about that, but you can see it. So if you see equation 2.67 in the book, it has a more general definition for strain. So what you see is that there are so many formulas for a strain tensor. And all that you want is that this strain tensor should vanish whenever you have rigid body motion, or whenever there is no deformation. This must vanish. And then you have all these definitions. Okay, so with this I'm going to end the class today, and that's also the end of chapter 2 from the textbook. Okay, So if you have any question, please feel free to ask me.
When can we use this LNU? Means it is increasing. Sorry, it is varying
Logarithmic,
quickly.
yeah, it's a logarithmic. There are some material for which the energy form is simpler when you use this logarithmic strain tensor, especially for soft materials. It turns out, or polymeric material, when you stretch it, no, it has that logarithmic type of nature. So energy, the stored energy for such material has a simpler expression when you write it in terms of ln of u. Okay, and that's why this that's also commonly used, that definition for strain. Any other question?
Part of the lecture, we obtained the F tensor in terms of the eigenvectors and eigenvalues.
um Let me go there. So are you talking about this formula? So if you're talking of this formula, then it's not so difficult to derive it. So you see, this is F is R times U, right? And U, we already saw it is summation over I, lambda I, little r I, tensor product little r I. So when it's pre-multiplied with big R, it simply goes here, and then it becomes summation over I, lambda I, big R into little r I, tensor product little r I. Okay, and this is what it is here. That big R little r I is same as Li. Yeah.
From R to V. So my question is, can you again explain that after operating the rotation tensor on reference frame, we are getting the intermediate term, and
Yes.
from and operating the V tensor on this intermediate term, we are getting the final most the deformed final from the current configuration. So in the
Correct.
last class, you said all those the L1, L2, L3, and remaining all the material lines will be stretched, and we will get the final deformed configuration, the
Correct.
rightmost. So
Correct.
you said uh, after operating the intermediate on the V tensor, only
Hmm.
the orientation of these three will not change, and
Correct.
rest all orientations will be changed. Also, they all get stretched. So can you again explain why the only three are not getting orientations and change?
Because these three are also the eigenvectors of V, no? These L1, L2, L3 are the eigenvectors of V. So V times an eigenvector is what? Is again along the eigenvector itself by the definition of eigenvector. So therefore V times L1 is again directed along L1 itself. It's simply lambda 1 into L1. And it's only the eigenvectors which will not change their orientation, right? Because by the nature of that eigenvector thing, V times Li is simply lambda I Li. So therefore, these three line elements do not undergo change in orientation. But for any other line element, because that won't be an eigenvector, so when you multiply that line element with V, it won't give you back a line element in the same direction because it's not an eigenvector, right?
Okay, so we
And
can say that
and V being a second order tensor in this dimension three, it has only three eigenvectors, and therefore it is only those three lines which do not undergo any change. Of course, if there are a special case when, for example, lambda 1 and lambda 2 are same, then any combination of L1, L2 is also an eigenvector. And in that case, you will have several line elements which will not undergo change in orientation. Yeah, now tell me.
So in the same way, we can also see the picture above it. So you will also transforming uh, the stretching these three only, the R1, R2, R3s. So their
Exactly.
directions will not be not change. All other
Ye-
material lines will change their orientations
That is true.
along with the stretching.
Along with stretching, yes.
Yes. Okay, sir. Understood.